Yeah, g'day, it's Charlie ZL2CTM. Well, I thought I would do an update today on what I've been playing around with in terms of the Franklin Oscillator. I've got it now to a point where I'm quite happy with where it's at and the frequency range that it's generating, which is good. So I'll just sort of run through that now in terms of what I got up to, and we'll go from there. So it's been quite interesting actually. It would appear that there's a number of different topologies when it comes to the Franklin Oscillator in terms of FETs versus BJTs, whereabouts the tank circuit is placed, and the numbers and configuration of the coupling capacitors from what I can see. I've settled on this particular one here, which has a couple of BJTs set up with the tank circuit in the middle, because to me it makes the most amount of logical sense. Yeah, I'm no expert in this in any way, shape or form, but it makes sense to me in terms of how this is actually working. So from what I can see, we have two BJTs here set up, and I'll go through the maths and what I did for the biasing for these, with our LC tank circuit in the middle. And when you first turn this on, there's no energy in the tank circuit, but this amplifier here is essentially amplifying noise, just white noise on the input, which is then seen on the output. Now one of those frequencies, or that white noise, is made up of many frequencies, one of which will happen to be the resonant frequency of the tank circuit. So some energy will be passing into the tank circuit to basically start to form essentially oscillations within that tank circuit. And those oscillations, or that energy within that tank circuit, is then being sampled through this capacitor, which I'll talk about later on, with then being amplified in this amplifier here, and then passed back through the feedback capacitor back through the input. And as long as the Barkhausen criteria is met, so a loop gain greater than 1 and our 360 degrees phase shift, which we do have, if that's increasing, this is decreasing; if that's decreasing, that's increasing, therefore it's in phase, we get our oscillations, our stable oscillations. So to me that makes perfect sense. And also this capacitor here needs to be very small, because we're just sampling just enough energy there to pass through without sampling it too much and distorting our waveform. And that I saw too, which was interesting. Anyway, so what I think I'll do at this stage is just talk about what I did for biasing, and then talk about some of the interesting parts, for example that capacitor there. So what I elected to do is, for stability and right or wrong, from a thermal's point of view, I wanted to minimize the amount of current passing through these two devices here. So I elected to not run with 1 amp or 10 amps, so I just sort of notionally chose 2.5 amps. So 2.5 amps, my goodness, 2.5 milliamps quiescent current passing through these two 2N3904 devices. Running it on 6 volts. So in terms of biasing, need to work out what our beta DC is. I just took that straight out of the spec sheet and just elected to use the geometric mean between the range that they provide for roughly 2.5 amps. In fact it's more like 10, but close enough. So 100 times 300 square rooted equals 173. So that's going to be close enough for this. And the other setting that I elected to use, right or wrong, was to set this point here just slightly above the halfway point between ground and VCC. So between 0 and 6 volts is 3, and just slightly higher than that. So I just notionally chose 3.5 volts to put that point there at. So in terms of resistors, first thing we need to know RC. So if that's at 3.5 volts and that's at 6 volts, and we've got 2.5 milliamps passing through it, then through Ohm's law, 6 minus 3.5 divided by 2.5, as we see down here, equals 1 k ohm. So that's nice and easy. Let me just see if I can rearrange this. Next was the fixed biasing resistor. So fixed biasing for this is that resistor just there, going between the base and the collector. I made these both the same for both devices. So how do we come up with that? So the formula is normally beta DC brackets VCC minus VBE, and I'll talk to that, divided by EIE minus RC. Now I've used VE for the simple reason that rather than having the emitter typically tied to ground for this, I've elected to put in a 10 ohm resistor on both sides just for a little bit of stability. So I need to take into consideration the voltage drop across that. Not huge at 2.5 milliamps, but might as well take into consideration. So rather than being like I say VBE, I've made that VE. So running through the numbers, let me just zoom out a bit there, hope that's still visible. So 173 VCC, 6 minus, now the voltage at the emitter, 2.5 milliamps times 10 ohms, divided by 2.5 milliamps, minus RC, which we just calculated before, which is 1K. Comes out at 192 k ohms, so I'm going to use the nearest standard value of 200k, and that's why we see 200k there and 200k there. And that's all from the resistor's point of view. Coupling capacitors, just the feedback, just using 100 picofarads coming out of that first amp just to provide a bit of energy into here, just 10 picofarads. And then comes CG. Now I've called CG for Gimmick because quite often for this particular circuit you'll see Gimmick capacitors used because the capacitance is typically less than a picofarad, which trying to find a lumped device for that is difficult. The lowest I can find is 1 picofarad. So typically a couple of wires twisted together is what's typically used. What I've elected to do for this particular case is I've used, and I'll just let me just zoom up there and hopefully you'll still stay in focus. You can see there in the middle is a piece of strip board just there. So it's basically the same strip board here, which I just run a razor blade down there and snap it off. I've used 2 tracks, and as you know, a capacitor is proportional, its capacitance is proportional to area. So the longer those 2 plates are side by side, the greater the area is of the capacitor, and if I shorten that down, the capacitance gets less, and that's exactly what I did here. So when I started with this little strip board here, it was out about 10 holes long. I then looked at the waveform, and the waveform was slightly distorted. I was taking too much energy out of that tank circuit, so I started to snip with a pair of snippers across the holes, and had another look, snip, 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 and as it turned out, each time I took one of those holes off the overall length, I reduced the capacitance by 0.2 picofarads. So now I got down to a point here where the waveform from my point of view is acceptable, as well as providing sufficient energy to go through to that second stage to ultimately then get passed back around through the jumper there back into the first stage, and that's what it is. So I think my calculations are it's sitting around 0.4 picofarads. So that's probably all to talk about that. So that then takes us on to the tank circuit itself. So you'll see down here I'm using a T68-6, a yellow core, so good for that sort of 10 to 40 megs. I think it is, yeah, was it? No, it might be actually 3 to 40 megs. Either way, I'm running this VFO at around 11 megs, so that's a good core for that. Right, so that introduces a few things now which I have to come back to the piece of paper, and that's, you know, what frequency do I want to run this at and why. I touched on it last time, but let me just reconfigure things here. As you know, I'm not into great videos in terms of cutting and splicing, so you get what you get. So IF of 10.7. Now you might recall from the last video that I mentioned I was going to use a 9 meg IF from a crystal filter. There was a question asked in the comments that was the 6 kilohertz bandwidth going to be sufficient for the broadcast band. My initial answer would have been yes, it's fine, because the station that I'm most interested in is basically our national program, which is predominantly voice. However, having said that, I did have in the junk box a 10.7 kilohertz, so again megahertz crystal, with a bandwidth of 7.5 kilohertz. So that additional 1.5k of bandwidth at the 3 dB point is, you know, slightly higher fidelity. So I'm going to use this one, which means then that my IF is now at 10.7. So from a calculations point of view, I need to, in fact I'll talk about it now, I need to have a VFO sitting on the high side of my IF. Now again, with that last video it indicated that it could have been either on the low side for low side injection or on the high side. I've gone with the high side for the simple reason it makes logical sense when it comes to actually dialing the frequency change knob here. When you go clockwise, the expectation is that you will then pick up a station which is higher up the broadcast band, and vice versa. When you go backwards, you should be picking up a frequency lower. If you have the VFO on the high side, it makes sense because you're using subtraction. So my VFO minus my incoming frequency equals IF. So it basically steps up in tune. So that one minus that equals that, and as I go up, that minus that equals that. If you're on the low side, so low side injection, it goes the opposite way around because you're using addition, and the higher the frequency you want to detect, the lower the IF needs to be. So you end up winding your VFO backwards to tune up to a higher frequency than what you want, which doesn't make logical sense. So that's the reason why I've gone for the high side. Okay, so what have I done then to choose the values of inductance? Because my inductance. Okay, full stop. So that variable capacitor over here ranges from, and I'm going to use both sides, 20 to 80 picofarads. So just to kick things off, I'm going to choose a value of halfway across that range of 50 picofarads, and then I'm then going to choose, okay, our frequency of oscillation is 1 over 2 pi root LC. I know what my C is, I've just determined that. My inductance is unknown, but what is my frequency? So my frequency I'm going to choose is what the VFO needs to be at the halfway point. So my actual range of frequencies I need, back on the first page, is down here. So there goes a range that we want to pick up, 540 kilohertz to 1.6 megs or 1600 K. I've just subtly brought that down a bit to get a good range, so I've gone from 500 up to 1650. So 10.7 plus a half equals 11.2, and 10.7 plus the upper end equals 12.35. So that's the range of VFO frequencies that I need to get out of the VFO. So picking a value halfway along there, I will just notionally pick 11.7 megs. So now we've only got one unknown in our formula, which is inductance. So rearranging that formula there to make our inductor the subject, and then plugging in those values, we come out with an inductance of 3.7 microhenries. And for a T68-2, say again -6 yellow core, that turns out to be 28 turns, which is what we see over here, 28 turns. So that's all great. But like any, well, in my experience, which is not a huge amount, but you need to add in some series capacitance with the variable capacitor, as well as some parallel capacitance, typically, to push and squeeze the VFO to get the frequency coverage you need. And what I mean by that is two things. There's stray capacitance and other things which invariably mean that your frequency won't be exactly what you need, so you need to trim it and add a little bit of capacitance or subtract a little capacitance to get that where you need. And the other problem is, in this particular case, my variable capacitor runs from 20 picofarads to 80 picofarads, and even if I was to halve that, I still have the same problem, which is that at the maximum capacitance and the minimum capacitance, the range is too great. So that's what I've tried to depict here. So that's the range of what I need to detect, and this is what my VFO is outputting. So I'm getting way more frequency variation than I need, which I just mentioned before was 11.2 to 12.35. So to reduce the range of frequencies that variable capacitor produces, I need to add in a little bit of series capacitance with it, and then once I've got that worked out roughly about where it needs to be in terms of the range, to shift it up and down the frequency axis, I do that by varying the parallel capacitance with it. And as Murphy's law, there is some interaction between the two. So when you tweak that, it shifts that one, and vice versa. But by full stop. So what I've done there, I've got two trim caps. So if we come back here, we can see those sitting there. Those trim caps run from 5 to 40 picofarads. So there's one here that's in series, coming out of the capacitor through that series trimmer to the tank, and then the other one is across the tank to ground. So that's the second trimmer. So that's the first one, and that's the second one. And by tweaking those, I can then get the range of frequencies and where they sit in the frequency spectrum to be pretty well spot on. So I'm getting a range now of 11.1 through to 12.3 megs, which is just on, it's just slightly more than what I needed. So in other words, I've got more than enough, which is good. Invariably things will change because I do need to put this into a box to give it some stability, and I will need to build the buffer amp. Now, I haven't talked about thermal stability. I am not too concerned about that. I'm not going for an ultra stable VFO, so I'm not trying to find negative temperature coefficient devices to offset positive and vice versa. I'm more than happy to tweak the frequency as needed during the warm-up phase, or if there was to be a massive thermal difference in the room for whatever reason, I have no problems adjusting the frequency. Each to their own, as they say. So that's that. Right. So next steps that I do need to do is I do need to add a buffer amplifier, because at the moment, if I was to go, the amplitude variation across the range is around 50 millivolts, and typically I'm sitting around 480 millivolts peak to peak. I do want to, and I am going to use a SBL1, which is a 7 dBm device. So I do need to ultimately have the VFO outputting 1.414 volts peak to peak across that 50 ohm SBL1. So I do need to follow this VFO as it stands, with at least an amplifier with a voltage gain to get it up to 1.414, and then I'll also have between that, let me just draw on a bit of paper, a buffer. So at the moment we have a oscillator, and over here ultimately we're going to have the SBL1 50 ohms. So I need to amplify this output, plus I want to provide some buffering between the load and it, so any variations here aren't going to wildly change the frequency over here. So I'll follow that first with a buffer amp, and then with an amp with some value of voltage gain to get it up to that 7 dBm into that 50 ohm load. So the buffer amp, I will make that a common collector. So again, I'm just going to use a 3904. I'll have the collector tied to VCC, and then we'll have stock standard voltage divider biasing, input on the base, and we'll take the output across the emitter. So that, looking into this way, which is where the oscillator is sitting, is a relatively high impedance, and that impedance doesn't vary with variations on the output. But as you can see, because the output's now sitting across the emitter resistor, that's going to be actually less than what's coming in due to the forward bias diode sitting in here. So the voltage gain is approximately 1. If not, it's actually subtly less than 1. So in terms of, again, trying to get up that 7 dBm, I'm going to have to follow this up with another amplifier. Another amplifier, which will make that a common emitter. I probably might go for an RFC in here, or a 4:1 transformer, so to transform that 50 ohms of the mixer, transform it up to that roughly 200 ohms for the load on that. We'll see how things play out there, and I'll probably have some kind of trimmer with a bypass cap there, 100 nanofarad bypass cap there, to vary the overall gain here. So I get that gain of this particular stage here to give me my 7 dBm. So we'll see how things play out there. But that's what I do need to build from this point forward and to add into here. Once I've built that, I will rearrange all this. This is just a temporary board on the bottom just to tack things down and have a bit of a play. And I'll basically rebuild that. Have the inductor nicely secured to the base so we don't get any mechanical vibrations upsetting things there. And basically have it inside that one overall box will be both the VFO, the buffer, and the buffer amps, plural, as an output. So that's the plan. That's the next steps. I may look to put a video up on that one. We'll see how things play out. Otherwise, I'll just go straight into the next phase. But we'll probably we'll see how things play out. Okay, I think that's all I wanted to touch on. Certainly an interesting amplifier, oscillator. It's been interesting to have a bit of a play around with it. Yeah, so hopefully that was of interest. And like I say, I'll say 73 here, and I will catch up with you at the next video. Before I go, I'll put everything up on the blog, so I'll leave that in the notes, and I'll just scan those calcs, put them up. Again, normal sort of public service announcement. I'm no expert in this. I'm not a lecturer, not a tutor. This is just the world according to me and how I see things, and we'll go from there. Okay, cheers all.